Yes, good evening all. So welcome to your new session, Mass Spectrometry 3. This is your third class of Mass Spectrometry. So those who are familiar with first class as well as second class, then this class will be very easy for you. Okay. So in your first class we discussed about Mass Spectrometry general introduction, then what is the general principle, then what are the applications of Mass Spectrometry. In your second class we learn how variable types of electrons are present in a given molecule, how to remove that electron, and what is a molecular ion and what is molecular ion with respect to a neutral molecule, with respect to a charged molecule that might be either positive or negative. So possibilities of generating all molecular ions and molecular species we discuss, starting from alkane to variable possibilities. So if any molecule having only sigma electrons, pi electron, non-bonding electron, like that, different possibilities we selected for the preparation of a molecule species. Okay. Next, after that, now we are going to discuss how to identify the stability of a molecular ion. Okay. So what is the use of stability of molecular ion in mass spectrometry? If any molecular ion is more stable, whose lifetime is increases. If lifetime increases, corresponding molecular ion is stable. So if any particular molecular ion stability increases, whose intensity is very high in mass peaks. Right or not? So what is the meaning of stability? Stability nothing but relaxation. Lifetime of any particular species is nothing but a stability. Okay. So keep hitting stability of molecular ion. Stability of molecular ion. What is the stability aspects of molecular ion? So what is the meaning of stability? We can define like this: lifetime of a molecular ion. Lifetime of a molecular ion is known as stability. Means how much time it will spend as a molecular ion without fragmentation. See, whenever if you apply electron beam on a given molecule, that molecule forms a radical cation. That becomes what? Molecular ion. So molecular ion further undergo fragmentation. So when molecular ion undergoing fragmentation, it will spend some time. How much time it will exist as a molecular ion? How much time it is taking? That is called lifetime. Suppose if lifetime is very high, fragmentation is very poor. If lifetime is very less, fragmentation is very high. Because if lifetime is very high, molecular ion is stable. If lifetime is very less, molecular ion is unstable. Unstable molecular ion undergo rapid fragmentation. Okay, more stable, poor fragmentation. That point you remember. If it is unstable, more effective fragmentation. So lifetime of a molecular ion is known as stability. Okay, so as stability increases, what happens to molecular ion peak? Molecular ion peak intensity increases. Okay, more stable molecular ion will give intense molecular ion peak. As stability increases, molecular ion intensity increases. Okay, now here we are going to discuss about factors. What are the factors influencing stability of a molecular ion? So try to understand what is stability of a molecular ion. The lifetime of a molecular ion is called stability. How much time particular molecular ion exists as a stable species. Suppose if molecular ion is maintaining more time, it is more stable. If it is spending less time, less stable. Okay, now factors. What are the factors influencing stability of molecular ion? First one. Okay, see, as number of carbons increases, in straight chain, stability of molecular ion, what happens? Stability of molecular ion decreases. You remember this point. This symbol indicates that decreases. Downward symbol indicates decreases. Upward symbol indicates increases, stability increases. As number of carbons increases in straight chain, stability of molecular ion decreases. Which means, suppose If I take methane, this is molecular ion, then followed by ethane. Now, between these two, which is the most stable molecular ion? Which is more stable molecular ion? See, as number of carbons increases, in straight chain, stability of molecular ion decreases. More number of carbons, unstable. So, which is more stable? Methane is more stable than ethane. Ethane is more stable than which one? Ethane is more stable than propane. Propane is more stable than which one? Is it butane or not? I am giving CH2 and here one more CH3 and this is the one. So this is more stable than this one. This is more stable than this. This is more stable than this one. As number of carbons keep on increasing, what happens to stability? Decreases. So this molecular ion lifetime is very less. This molecular ion lifetime is very high. If lifetime increases, then what happens? Fragmentation decreases. Here lifetime is very less or not? So they undergo very fast fragmentation. Try to remember. First our target is to generate molecular ion. After generating molecular ion, think about stability. If it is highly stable, less fragmentation. If it is unstable, more fragmentation. So in your examination, gate examination, this point is given. Which among the following molecular ion is highly unstable? Out of this, which is highly unstable? Last one. Which will give more information about structure? Last one. Whichever molecular ion is unstable, that will give more information about structure. Clear? First factor, as number of carbons increases, in straight chain, stability of molecular ion increases. Here you write, stability of molecular ion decreases. More carbons, less stable. As number of carbons increases in straight chain, stability of molecular ion decreases. As number of carbons increases, molecular ion becomes unstable. Second factor which will influence the stability of molecular ion. See, as branching increases, stability of molecular ion decreases. As branching increases, stability of molecular ion decreases. So, see, I am taking a pentane. Pentane means how many carbons? 5 carbons or not? See, here I am taking a straight chain pentane. So this is molecular ion. Now I am taking one more, which is a isomeric of this one. Here how many carbons are present in this one? Here also 5 or not? So this is your first molecule and this is your second molecule. With same molecular formula? Molecular formula remains same or not? I am taking third molecule which having 5 carbons with more number of branches, CH3 and here one more CH3 like this. This is 3. 1, 2, 3. So, here molecule having same molecular formula but differ in their branches. Here 5 carbons, no branch. 5 carbons, 1 branch. 5 carbons, 2 branches. As number of branches increases, stability of molecular ion decreases. This is decreasing. So, I can say which is more stable? Which is more stable? First one is more stable than second one. Second one is more stable than which one? Third one. So finally if you consider the stability factor, 1 is greater than 2, 2 is greater than 3. So which will give more information about fragmentation? Third one will give more information about fragmentation. So this is highly unstable molecular ion. So what is the difference between this one and this one? Here only straight chains. Straight chains with dissimilar number of carbons and hydrogens. 1 carbon, 2, 3, 4. But here, everywhere 5 carbons only. 5 carbons, 5 carbons, 5 carbons. But what happens? Straight chain, only 1 branch and here 2 branches. This is 1 branch and this is 2 branches. Clear? Right. As branching increases, stability of molecular ion rapidly decreases. Clear? Next, third point, C. As molecular weight of molecular ion increases, what happens to stability? Stability decreases. If any molecular ion having more molecular weight, sometimes in mass spectrometry, that molecular ion peak will be disappear. It is impossible to identify molecular ion peak because peak intensity depends upon stability or not. Suppose I am taking a bulky molecule, very large size molecule is there, whose lifetime is very less. If lifetime is unable to identify, whose peak intensity is almost all negligible in mass spectrometry. Sometimes peak cannot be appeared. Okay, so I can say that as molecular weight of any molecule molecular ion increases, then what happens to its stability? Stability decreases. Example for this case, we can take any steroid. Okay, steroids, and we can take a terpenoid, and we can also take even sugars, etc. Sugars and carbohydrates, if you take, almost all molecular ion peak is not available in mass spectrometry. If you take any steroid, bulk structure is there or not? Terpenoid also bulk structure. If you take any sugar, any glucose, fructose, mannose, you take any tetroses, pentoses, hexoses, etc. If you take any one, in that one, due to presence of more number of carbons and bulky functional groups, on that time, lifetime of molecular ion is very poor. If lifetime is very poor, spontaneously that molecule will undergo molecular ion formation, suddenly it will disappear. Lifetime is very poor. So, if I take any molecule by using 7 to 15 electron volts, then what happens here? This is a molecular ion. Now what about this? High molecular weight is there. If molecular weight is very high, then what happens? This is found to be unstable. Unstable means very fastly undergo fragmentation. If this is stable, peak intensity increases. If this is unstable, peak intensity decreases. Finally it will disappear. So if you want to get mass spectrometry, mass signal, see this is m by z and this is percentage of intensity. Suppose see, if this molecular ion is stable, here see this is your molecular ion peak or not, always molecular ion peak is at last. Over here molecular ion peak. Now this intensity, this height depends on the stability. Suppose if molecular ion is stable, then what happens? Intensity increases. Suppose if this formed molecular ion is unstable, then what happens? Slowly height decreases. Height will be slowly it is decreasing. Unstable, unstable, unstable like this. Finally at one particular stage it will disappear. It is appeared actually. In core it is appeared. But if you see generally it is looks like it is disappear. See actually one point I given. But you people think that it is not a mass peak. But actually one peak is there, but that is not easy to identify. So this peak intensity always depends on which one? Molecular ion peak is always depends upon the corresponding structure. If any open chain is there and any branch is there, any high molecular weight is there, so that will be rapidly affected. Especially if molecular ion having high molecular weight, whose mass peak, this is called mass peaks, that is start disappearing out. Sometimes it is not easy to identify in mass spectrometry. You people think that last peak is always mass peak. That is not correct. Sometimes this peak will be disappear out. Okay, very poor mass peak. Here you write. So this peak is sometimes it is disappear. So this is poor molecular ion peak. Peak is very weak. It is start disappearing out. If this weight is keep on increasing, even this point also not possible to identify. If it is lightweight is there, weight is very less. On that time, intensity is very high. Remember, only one point you remember in mass spectrometry. Stability directly proportional to intensity. It may be a molecular ion, it may be a fragment ion. It may be any one. As stability increases, molecular ion peak intensity increases. So this point is commonly applicable for steroids, cholesterols, terpenoids, and even for alkalides also we can apply. Alkalides and sugars, many bulk molecular weight carbonyl groups are present, and bulk molecular weight functional groups if they are present, so whose appearance is almost all disappear. Clear? Try to understand the points simultaneously, it will be easy for you. See, unsaturated molecular ions are highly stable over saturated molecular ions. Unstable molecular ions are more stable than saturated molecular ions. You know, suppose if I take carbon oxygen double bond, here one carbon one oxygen is there, it is molecular ion. This is found to be more stable as compared to molecular ion having saturation. This is stability order. Here how many carbons are present? One carbon. How many oxygens? One oxygen. There is a double bond is present. If double bond is present, that is found to be stable. There is no double bond, unstable. So between these two, which molecular ion is stable? This one. Clear? So remember, unsaturated molecular ions are more stable than saturated molecular ions. Clear? Unsaturated molecular ions are highly stable over saturated molecular ions. Then see, if I take any conjugate molecular ion, conjugate molecular ions are highly stable over unconjugate molecular ions. Unconjugate molecular ions. If any molecular ion having conjugation, that is found to be more stable. Okay, suppose if I take carbon carbon double bond, see here how many double bonds are present? Two double bonds. Is this two double bonds under conjugation? Yes. See, when sigma bond and pi bond both are present, from which electron should I remove electron? Should I remove electron from pi or not? Yes. So here conjugation is there. In this any conjugation is present. In this case, this is CH2 and here one more CH3. Here also molecular ion. Here two double bonds under conjugation, but there is no conjugate. If there is no conjugation, corresponding molecule is found to be unstable. So which is more stable here? Conjugate olefins are more stable than unconjugate olefins. Greater the conjugation, greater the stability of a molecular ion. More conjugations, more stability. Suppose if I take three double bonds under conjugation, this is more stable than two double bonds. Then this is more stable than. Six carbons are there or not? Here 6 carbons, molecular ion. Here 6 carbons, molecular ion. Then here 6 carbon, molecular ion. But what is the difference? Here conjugation is there, here conjugation is very poor. And here there is no conjugation. First of all, there is no multiple double bonds. So, as conjugation increases, what happens to stability? Stability also increases. as conjugate molecular ions are present whose stability is found to be very high. So here I can take one more, here double bond molecular ion, and here one more double bond molecular ion. Which is more stable among these two? First one is more stable or not? First one is more stable than second one. B. What is the reason? Conjugation is there. So now this is aromatic. Aromatic. Here two double bonds under conjugation, and here one double bond is in this. So which is more stable? First one is more stable than second one. So here see, this is aromatic, right or not? So aromatic molecular ions are more stable. Initially aromatic molecular ions. Aromatic molecular ions are more stable than anti-aromatic molecular ions or non-aromatic molecular ions. This is gate question. In gate this is given. So one of the entrance examination it is given. So this is double bond, and here it is one more double bond, and here one more double bond. Which is more stable? Which is more stable? Second one, molecular ion. This is I am writing as a molecular ion. So second one is more stable than this is second. Then first one. First one is more stable than third one. Here more availability of pi electrons, less availability of pi electron. Clear? So finally see, this is your last application. If I take a molecular ion of cycloalkane, more stable, it is more stable over alkane. If you compare molecular ion of alkane and cycloalkane, always cycloalkane molecular ion is more stable. If I take similar number of carbons, see, this is 6 carbons are present or not in this cyclohexane. This is molecular ion. This is more stable than which one? 6 carbon open chain. Acyclic and alicyclic. Acyclic is this one. This is called alicyclic. Acyclic means absence of ring. Okay. So always 6 carbon ring is more stable than open chain. Suppose if I take 5-membered, cyclic or not? Cyclic. Always cyclic will give more stability, stable molecular ion as corresponding open chain. Remember, if any competition comes between open chain and rings, give priority for rings. If you compare same number of carbons. So 6-membered ring, open chain 6. 5-membered ring, open chain 5. So this is more stable as compared to this hydrocarbon. Clear? So that is about molecular and stability. Variable factors I explained. So this is Beeman order of molecular and stability. This order you need to remember. It is given in your variable test books with a proper order. Okay. Molecular and stability by following Beeman, proposed by Sir Beeman. That's why it is called Beeman molecular and stability. Okay. So mostly we are following this Beeman order only. So which is more stable? This is all our molecular ends only. Aromatic molecular ends. Every time you write molecular end is more stable than conjugate olefin. Conjugate olefin molecular end. Conjugate olefin molecular end more stable than olefin molecular end. Then cycloalkane. Cycloalkane molecular end. Every time you write molecular end like this. Cycloalkane molecular end. Then followed by unbranched molecular end. Unbranched. What is the meaning of unbranched? Unbranched means open chain. Open chain. Okay. So then followed by aldehyde. Aldehyde molecular end. Then amine molecular end. Okay. So after amine, go through carboxylic acid. Carboxylic acid molecular end. Ester molecular end. This ester molecular end is more stable than branched alkane. Branched ion molecular end. Then followed by alcohol. Alcohol is more stable than ether. So this is molecular and stabilities. So this is more or less almost all equal. Alcohol and ether depends upon the skeleton. Sometimes ether and alcohol having same molecular and stability, but least priority goes to alcohol and ethers. This is proposed by Sir Beeman. That's why it is called Beeman molecular and stability. Roughly it is given because there is no proper functional group here. Means many aromatic molecules are there, many conjugate olefins are there, 1 conjugation, 2 conjugation, 3 like that, so we can't compare, but in generally conjugates are more stable than simple olefins, only one double bond. Then followed by cycloalkane, rings, then open chain, unbranched nothing but open chain, straight chain, then followed by aldehyde amine acid ester, aldehyde amine acid ester, so branched alkane, alcohol and ether. You remember this order. Carboxylic acids, esters, branched alkane, then alcohol and ether. Beeman order of molecular and stability. Clear? So that is about stability of molecular and next is recognition of molecular and peak. How to identify molecular and peak in mass spectrometry? Recognition of molecular ion peak. Up to now what we learn? What is a molecular ion? How to generate a molecular ion? What is the stability of a molecular ion? Variable factors I explain for generating a stable molecular ion. First one is what? Open chain, then branched chain, then followed by rings, then conjugate, then unsaturated functional groups, then aromatic and rings, etc. So then after that I given beam in molecular order of stability. Then what is this? Recognition of molecular ion peak. So what is molecular ion peak? So molecular ion peak is nothing but in mass spectrometry, the peak which is appeared at last in mass spectrometry, that peak is most commonly behaves as a molecular ion peak. So that molecular ion peak intensity depends upon the which one? Stability of molecular ion. If molecular ion is more stable, peak intensity is very high. If molecular ion stability decreases, peak intensity also decreases. So now thing is, in general, last peak in mass spectrometry belongs to it belongs to molecular ion peak. In generally what happens? See, because here in mass spectrometry, peaks are represented based on their implicit value. Right? Peaks are represented by implicit value. So which one will be written at last? The peak which having high implicit value. But each and every fragment is coming from which one? Each and every fragment coming from molecular ion. So always molecular ion peak will be represented at last in mass spectrometry. Right or not? So that is called high mass region. High mass region. See, all fragments are coming from which one? All fragments are coming from molecular ion, or it is coming from fragments? They are coming from molecular ion. So means molecular ion having always high implicit value. So always molecular ion is represented high mass region. High mass region nothing but the molecular ion implicit value becomes very high. So finally only one conclusion you remember, always in mass spectrometry at high mass region molecular ion peak is represented because it is a source for variable fragmentation. So whichever is a high mass region, that is called parent. Molecular ion is a parent. From parent what we are getting? Fragments. Fragments are nothing but daughter. Okay, now parent ion is what? Molecular ion. What about daughter ions? Daughter ions are nothing but a fragment ions. Always daughter ions are coming from which one? Parent. Always daughter represented by lower mass region, parent represented at high mass region. Clear? Right. Keep getting recognition of molecular ion peak. Write down. In mass spectrum, molecular ion peak represented at high mass region. High mass region. In mass spectrum, molecular ion peak is represented at high mass region. In mass spectrum, molecular ion peak represented at high mass region. So what about intensity of parent ion? Intensity of molecular ion depends on which one? It is depends on stability. I want to write the intensity of molecular ion, that is depends upon stability. Intensity of this molecular ion depends on stability. Greater the stability, greater the intensity. Okay, so generally this is molecular ion I am writing. This is implicit value and this is percentage of intensity. Now this is molecular ion. I am writing more intense molecular ion. Intense molecular ion. If it is an intense molecular ion, it is found to be stable molecular ion. Stable molecular ion will give poor fragmentation. What about this all are? If any peak represented at high mass region, that is called molecular ion. And if I written any peaks left side of molecular ion, this all are belongs to daughter ions. These all are daughter and this is parent. Suppose the parent having high intensity, daughter having low intensity. Sometimes even daughter having high intensity possible. And one more possibility I am giving. See, here I am writing implicit value and here percentage of intensity. Now molecular ion peak is very less. Then what about daughter ion peaks? Daughter ion peaks are little bit higher. So If I say if molecular ion is unstable, it is unstable, one of the fragment ion is highly intense. Daughter. This all are belongs to what? This all are daughter ion peaks. They are daughter ions or daughter cations. And this is parent. This is parent ion. We can also say parent. This is parent. Molecular ion is also called parent. If parent height is very less, daughter height, one of the daughter, because many fragments are possible. Daughter may give one more fragment. This is parent. Parent giving this fragment giving this one, this is giving this one, like that, back to back. Okay? So, if molecular ion is more stable, corresponding fragment ions are found to be less stable. If molecular ion is unstable, one of the fragment ion may be highly stable. And whichever ion having high peak intensity. So see, in this case, I am writing this is daughter. All daughter ions having very small heights. But what about parent? Parent having high height. So out of this all, which fragment having more intensity? Molecular ion or not? That is called base peak. That is a base peak. You remember this? I will explain later. In mass spectrometry, the peak which having high intensity is known as a base peak. The peak having lowest intensity, they may not be a base peak. They all are called, maybe a fragment ion peak, maybe a molecular ion peak. Don't think that always intense peak is a molecular ion peak. Sometimes intense peak may be a daughter peak. Sometimes intense peak may be a molecular ion peak. But only one point right now you need to remember for this concept. Always last peak is a molecular ion peak. So why it is a molecular ion peak? Why last peak is a molecular ion peak? Because we are taking a fragment with the help of a molecule. Right or not? So when you take a molecule embased value and molecular and embased value almost all same. Molecule and molecular ion, what is the difference? Only one electron. So mass is almost all same. So what is the reference from daughter? Reference for daughter is always original molecular ion. Means I am taking any fragment with the help of which one? Molecular ion. So then molecular ion having a highest weight or not? Molecular ion carry highest weight, that is represented over here. Means we are doing fragmentation initially from parent only. Then parent weight is very high every time. See, initially we taken 50 grams of one particular sample, 50 grams. I want to do fragmentation. If I remove a pinch, a small amount or small pitch of corresponding sample, then what happens to weight of parent? Decrease or not? 50 grams to 49 grams. Then 50 grams to 30 grams, 20 grams, like that. Means what is the reference? 50 grams. Parent is the reference. So that's why this is called high mass region. These all are low mass region. High mass region nothing but embased value is very high. Low mass region nothing but embased value is less. Clear? In mass spectrometry or mass spectrum, molecular ion peak is at high mass region always, but generally intensity of molecular ion depends upon their stability. Okay, always last peak is in generally it is a molecular ion peak. Okay, but remember always last peak is not a molecular ion peak generally. Generally, according to our calculations, what we are thinking, always last peak is a mass peak or not, molecular ion peak or not. Always last peak, this mass peak is belongs to molecular ion peak, but that is not correct. Okay, so don't think that always last peak is a molecular ion peak. Some differences will be there. So what are the different possibilities? What are the misleadings to confirm that last peak is not a molecular ion peak? Generally what we are thinking, always last peak is belongs to molecular ion peak, but that is not correct. Some mistakes will be there, especially some selective misleadings. Generally we can't say mistake, they are misleadings. Misleading is nothing but we are guessing that last peak is mass peak, molecular ion peak. But sometimes what happens, see, due to some common mistakes by observer, last peak is cannot be a molecular ion peak. So three possibilities are there. So they are called misleadings. Misleadings of last peak. What are the misleadings? Okay, don't think that last peak is a molecular ion. First misleading here, see. If sample molecule having impurity, then last peak is which one? Last peak is impurity peak. Is it a molecular ion peak? No, it is impurity peak. Remember, if sample molecule having any impurity, you need to take a pure sample. Suppose if any impurity is there, you will not get a last peak for molecular ion peak. That may be a impurity peak. Right or not? See, best example for this one, see, I taken benzene as a sample. Benzene. Example, benzene in toluene. But you don't know I added toluene. I say that I given benzene to you. But I know one secret, that without knowing you, I added toluene in that one. Toluene, methyl benzene. But you are saying that, sir, last peak is benzene. But I know that it is not benzene because toluene having high M/Z value as compared to benzene. Is it a misleading or not? Okay, so what is your first confirmation? Try to take a pure sample. Suppose if any person is given an unknown sample for you, and if you don't know what is added in that one, so don't think that based on that we can't say it is a molecular ion peak. Last peak may be impurity peak. See, I am adding benzene in toluene. So this is benzene, and what about this one? This is pure. It is a pure. Okay, and this is impure. This is M/Z value, and this is percentage of intensity. Example, what we are adding? Benzene in toluene. I am using this one. But what I am saying, I given benzene for you. I given benzene. But what I am saying, I not given toluene. I simply am saying that I given benzene, try to calculate mass peak. But see, this peak, this last peak, what you will think? This last peak you will think benzene. But why? You don't know that impurity is present. Right or not? So, but what is actual sample? Actual sample is benzene. But what about here this one? Toluene. Toluene is an impurity. Toluene is an impurity which is added in benzene. I recorded a spectra of benzene. So I can mislead that this last peak belongs to which one actually? If I not confirm that I added toluene, then what you will think? You will think that last peak belongs to which one? Benzene. But actually last peak is which one? Toluene. So that is one misleading. Okay. So this last peak is what? Impurity peak. This may not be a molecular ion peak. Sometimes it is an impurity peak. But what about this one? This is called molecular ion peak. This is your molecular ion peak. That is benzene peak. This is benzene and this is what? Toluene. Toluene is a impure proportions which are added to benzene. Clear? Is it a last peak is a molecular ion peak every time? No. If sample is pure, If sample is pure, then what happens? Last peak is a molecular end peak. This is the first misreading. Right. If sample molecule having impurity, then last peak is impurity peak. Example, benzene is a sample, toluene is a proportion which is added to this one. So this is sample. This is sample and this is impurity. Impurity added. My target is benzene. My target is not toluene. What is implicit value of benzene? 78. Implicit value of benzene is 78. So here this is not appeared at 78. If sample molecule having any impurity, last peak is appeared as a impurity peak, it is not a molecular end peak. Second possibility. Okay. Suppose see, if sample having any isotope, any heavier isotope, then last peak is not a molecular end peak. Last peak is not a molecular end peak. Then what about last peak? On that time last peak is isotopic peak. In this case, what about last peak? So here last peak is isotopic peak. So isotopic peaks are appeared after molecular end peak. Remember, last peak is what? Isotopic peak. So always M-based values are calculated by lighter isotope only. For any given molecular and M-based value I am calculating. Carbon, what is the lighter isotope? Carbon C12. What is heavier isotope? C13. Suppose if I take oxygen, 16, O16. What if it heavier isotope? 18, 17, all are available. Okay. So while calculating M-based value for any molecule, molecular ion or any fragment, always consider lighter isotope. Why we are considering lighter isotope? Why not heavier isotope? Because lighter isotope having more abundance in earth crust. Suppose if you are extracting carbon from anywhere, so maximum cases C12 will be available, but not C13. Because C12 availability is very high as compared to C13 in earth crust. So while calculating mass of any particular element, always try to consider lighter isotope mass. Don't take heavier isotope. Suppose if I want to calculate CH4, M-based value, CH4 molecular ion. Then what is the mass of CH4? M-based value? 12 plus 4 how much? 16. Why I taken 12? Carbon 12. Okay. So in earth crust, if you consider any carbon, if it is available, that is always available in the form of C12, but not from C13, whose availability is very poor. C13 availability is very poor, that's why we are ignoring it. Always remember only one point. Every element having more than one isotopes. Is it right? Only one isotope is possible or more than one isotope is possible? Every element having more than one isotopes. What is isotope? Same atomic number, but differ in their mass number. Atomic number is same, but mass number is different. So they are called isotopes. So while calculating mass of any element, try to take lighter isotope mass. Don't take heavier isotope mass. Suppose if I taken benzene here I taken benzene. What is M-based value of benzene? 78. Now whether I taken carbon with 12 or carbon with 13? Carbon with 12. Why not 13? Why I not taken 13? Because it is a heavier isotope. If it is a heavier isotope, why we are not considering? That is the question. You may ask one more question, sir. Even though it is heavier isotope, why you are not including in calculating M by Z value? Reason is lighter isotope abundance is very high, more than 90% for maximum elements. For maximum elements, lighter isotope abundance is very high as compared to heavier isotope. Okay, that's why while calculating M by Z value, always try to consider lighter isotope M by Z value only. Don't take heavier isotope M by Z value. Okay, so if any sample having isotopes, two isotopes are there. One is lighter isotope, heavier isotope. Whenever if you are taking heavier isotope, on that case last peak is not a molecular ion peak. Then what about last peak? Last peak belongs to isotopic peak. That is not molecular ion peak. Clear? So least availability belongs to heavier isotope. More availability belongs to lighter isotope. Whichever is more available, that mass is includes on particular element in calculating M by Z value. Okay? So always remember, lighter isotope mass is added in calculation of M by Z value. Always lighter isotope mass is added in calculation of M by Z value. Suppose see, if I take carbon C12, is it lighter or heavier? It is lighter. And what about C13? It is heavier. So between these two, which one is considered? C12 is considered but not C13. While if I given carbon add 12, don't add 13. Why? It is more abundant. Suppose if I take hydrogen, if it is hydrogen, then see here deuterium is there and tritium is there. This is 2 and this is 3 and this is 1. Now which should I consider? Hydrogen 1. Don't consider D2, T3. Suppose if I take oxygen how much here? 16. And see, even O17 is available, O18 is also available in earth crust. But I am not taking O17, O18 because availability is very poor. And what about this one? Oxygen. Suppose if I take chlorine, one more example. So this is chlorine, this is 35. One more chlorine is there, 37. Which is heavier isotope? This is heavier isotope. This is lighter. So take lighter, don't take heavier. Suppose if I take bromine, what about bromine? 79. And here bromine, what? 81. Okay. So take bromine 79, don't take bromine 81. Clear? So what are lighter isotopes? These all are lighter isotopes. Chlorine 35, bromine 79. Bromine is very, very important. So what is the difference between C12 and C13? 1 or not? So that's why it is called M plus 1. What is M? Molecular ion. This is plus 1. What is the difference between O16 and O18? How much difference? 16, 18, how much difference? 2. M plus 2. This is M plus 2. And here bromine 79, 81. How much difference? 2 or not? 79, 81. Difference is what? 2. In molecular ion, which one is added? 79. Then what is the difference with this? 2. That's why M plus 2. M plus 2. M plus 2. Clear? Suppose see, I given methane. How to calculate M-base value? Mass of carbon is what? Can you take 12 or 13? 12 only, don't take 13. If I take hydrogen, this is called 1H1, 1H2, 1H3. Deuterium and tritium, these two are heavier isotope. And what about hydrogen? Lighter isotope. Which one should I consider? 1H1 only. So, in this one, can I take M-base value like this or not? M-base value, how much? 12 plus 4, how much? 16. Suppose see in this CH4, same sample, suppose if C13 is present. C13 is present. Now what about this? It is a molecular ion or not? I can write molecular ion as M. Now in this CH4, some amount of C13 is there. This carbon is not pure C12, some amount, one fraction amount, 1.01 amount of C13 is present. Then how to calculate M-base value? M-base value is, here carbon is C13, here what is this? C12. So C13 value is how much? 13 plus 4. How much? This is 17. What is the difference? 1 or not? So it is M plus 1. But this availability is not exists. Almost all 99% of sample belongs to C12 only. If they not mention anything, take C12. If they mention any star, take C13. In your examination, don't confuse. Don't confuse if they given CH4. If CH4 is given, take lighter isotopes only for all elements. Don't take heavier isotope mass. Okay? Suppose one more example I will give. See, carbon monoxide I am giving. Carbon monoxide. Then what you will take? What you will take? How to calculate M-base value? So can I take 12 plus 16? Carbon is 12, oxygen is 16. So 12 plus 16 how much? This is 28. Now this 28 is belongs to M. This is molecular and M-base value. Always take which values? Lighter isotopes only. Now I am taking heavier isotope. What happens if heavier isotope is given? Then what about heavier isotope here? CO. Carbon may be 13 or not? Carbon may be 13. What about oxygen? Oxygen may be 16. Okay. So I can take carbon 12. Then what about oxygen? Oxygen may be 17. Then if you see these two possibilities, what about M-base value? 13 plus 16, 12 plus 17. Total how much? 29 or not? So now this is 29. What is the difference between this and this? 1. So I can write M plus 1. Right? And one more possibility. See, here carbon, oxygen both are present. Carbon is 12. This is 12. Then what about oxygen? That is 18 I am writing. Is it oxygen heavier isotope? But what about carbon? Lighter isotope. If you take any particular molecule, they should not carry heavier isotopes. All will be lighter isotope. If you take all lighter isotope M-base values for any given molecule, all lighter isotopes for given molecule, so blindly remember that becomes M-base value of that molecule. Okay. So in this case, what about M-base value? M-base value is 30 or not? Now what about this peak here? This is M plus 2 peak. If you add 28 plus 1, 28 plus 1, 29. 28 plus 2, 30. So what about these two? These two are belongs to isotope molecules. Then what is this? Simple molecule. You need to know this one. From these questions are coming. Only isotope questions are coming in your examination. Bromine heavier isotope, lighter isotope. Even last year also, this year, in December also one question is given. Bromine question. Are you written CSR? Are you written CSR examination this time? No, okay. So, one question is given which is related to bromine. See, this molecule is given like this. And here this molecule also they given. Here bromine, bromine, and here bromine. These two molecules are given. And they ask what is the intensities of these three peaks, intensity ratio of these two molecules in mass spectrometry. These two molecules they given, and question is like this. Identify the intensity ratios of these two molecules in mass spectrometry. Intensity ratios they are asking. So remember, bromine lighter. Lighter means how much? 79. Bromine lighter, 79. Suppose out of these two, one is lighter, other is heavier. Then 79, 81. One more possibility. 81, 81 or not? Two heavier. Two lighter, one heavier, two heavier. Total how many? Three. One is molecular ion peak, two are isotopic peaks, M plus 2, M plus 4. This you will understand later. Right now remember, M is nothing but molecular ion having all lighter elements or lighter isotopes. So don't add heavier atom MZ value in calculation of MZ value. Always take lighter atom or lighter isotope MZ value only. Okay. Suppose if I take mass spectrum of this one, see, this is MZ value and this is percentage of intensity. Now here MZ value is how much? First I written 16. For which one? CH4. Okay. So this CH4 I written and this is 12. Then what about one more? This is MZ value is how much? 17. And what about this? CH4 13 they given. Now this peak is belongs to what? This is belongs to M plus 1. And what about this one? This is belongs to M. M nothing but molecular ion. So now what about this peak now? This peak is belongs to, this is called isotopic peak. Is it isotopic peak is appeared at last? Isotopic peak is appeared at last. Is it a molecular ion peak? No, that is one drawback. That's what I am saying. Always last peak is not a molecular ion peak. Maybe a impurity peak, maybe a isotopic peak. So I want to remove this isotope. If I remove isotopes, what is your answer? If I remove this isotopic peak, then what is last peak? This one. Then this peak is belongs to molecular ion peak. That is simple. Okay. Now, one more possibility. Here this is M-based value and this is percentage of intensity. Now, here I am writing CO. CO lighter isotope. How much? 28. 28 means what is the possibility? CO. Now this is 12 and this is 16. Okay. So then one more possibility, you will get 29. This is 29. Then what about 29 here? C13 O16. C13 O16. Okay. Then one more peak is there. Now plus 2 difference here. So this is 12 and this. Now I am writing this is 18 and this is 12. Now what about this peak? This peak is molecular ion peak and this is M plus 1 peak and this is M plus 2 peak. So now these two peaks are belongs to isotopic peak. Isotopic peak. See, one more peak is also I can write. See, this is 30 or not? This is 30. Suppose see if I write C13 O18, how much? C13 O18. 31 or not? Here M-based value is 31. Then even this is also belongs to isotopic peak. Now, how to represent isotopic peaks? Isotopic peak is lighter atom M-based value plus the difference. Now, always isotopic peaks are represented by M plus 1, M plus 2, M plus 3, etc. Clear? So, if you take any sample without any isotope, if you take any sample without any isotopes, then last peak is belongs to, this is belongs to molecular ion peak. But this all are belongs to isotopic peaks. Clear? Right. Okay. So that is second misleading. Okay. First misleading is what? Misunderstanding, nothing but misleading. First misleading, impurity. Second misleading, isotopes. Third one, here one more peak you will expect, that is molecular ion collision peak. Molecular ion collision peak. This is also one more misleading. Last peak may be impurity peak, last peak may be isotopic peak, last peak may be molecular ion collision peak. Don't think that last peak is mass spectrometry molecular ion peak. Okay? If these three misleadings if you remove, then only last peak is belongs to molecular ion peak. Clear? Suppose, see, best example I am showing, see, this is one ether. This is one ether. Now ether upon electronic impact, by maintaining 7 to 15 electron volts, one of the electron is removed, then what you will expect here? There is a formation of molecular ion. Right? Is it a molecular ion? Is it a molecular ion or not? Yes, it is a molecular ion. 7 to 15 electron volts I supplied here. By removing one of the electron, there is a loss of electron, forms radical cation. Okay? Now this radical cation molecular ion is going to collide with one neutral molecule among this. See this. This is a molecular ion or not? This is molecular ion. Okay? The formed molecular ion is going to take one of the hydrogen from molecule. This is molecule. Here how many molecules are present? N number of molecules. In n number of molecules, some molecule forms molecular ion by losing one of the electron. This molecular ion is going to cleave one hydrogen from alpha carbon of neutral molecule. Clear? Then this hydrogen migrates from here to here. If this hydrogen migrates, then that oxygen is going to take that electron and forms H, and this is plus, and here lone pair. And what about next one? Here there is a formation of CH3O. Can I write CH2 dot or not? Can mass spectrometry can identify this one? No. Can identify this one or not? Now, but this is coming from which one? This is coming from which one? This is coming from collisions between molecular ion and what is this? Molecule. Now these two are colliding together. On that time, alpha hydrogen migrates from neutral molecule to molecular ion. Then molecular ion will take that hydrogen, forms a M+1 peak. Is it isotopic peak? Is it isotopic peak? No. Then what is this peak? This peak belongs to molecular ion peak. So M+1 peaks are not always isotopic peaks. They may be collision peaks. Is it collision peak or not? See, try to understand. Suppose if I not written this N, you will get some confusion. I written N. What is the meaning of N? N number of molecules are present. Here N number of molecules are present. In these few molecules, interacts with 7 to 15 electron volts, forms a molecular ion. Few molecules does not take this energy and they will exist as a neutral molecule. Right? See, I am applying 7 to 15 electron volts. Here how many molecules are there? N number of molecules. All molecules never shows molecular ion at a time. Few molecules, whichever they will bombarded, only that molecule will form a molecular ion. Suppose here just take 10 molecules are there. 7 molecules forms this type, remaining 3 as it is. They are not bombarded with this energy. Energy is there, but they are covered by some other molecules. Whichever molecules are not bombarded, they will exist as it is. That molecule collide with molecular ion. That collision is responsible to abstract one of the alpha hydrogen over here, then finally forms a M+1. Is it a molecular ion now? No. Is it molecular ion disappears? Yes. Initially this is molecular ion. Molecular ion is not undergoing fragmentation. Then what is going on? Molecular ion is not undergoing fragmentation. What is going on here? It is undergoing collision. So when formed molecular ion, before undergoing fragmentation, if they collide with neutral molecule, additionally you will get one more peak. That peak is called M+1 peak. That M+1 peak is produced by molecular ion collisions. So this kind of peaks appeared most commonly in ethers. It is also appeared in nitrile. It is also appeared in nitroalkane. Only these selective functional groups, this kind of interactions are observed. Clear? Is it M+1 peak is isotopic peak? No, not always. Sometimes it is isotopic peak. But right now it is collision peak. So I will give a rough example over here. This is M by Z and this is percentage of intensity. This is molecular ion. So what is a molecular ion? This one. Then what about M+1? This is O and here one more CH3 and here hydrogen and this is plus. What about this peak? This peak belongs to M plus 1 peak. You can write in close brackets also. Don't think that close brackets is molecule, molecular and collision peak. Right? What is this peak? What is M indicates? Molecular ion. Don't think that M is gaseous molecule. M should be taken as a molecular ion. Because molecular ion may be neutral, without charge. Molecular ion may be anion. Molecular ion may be radical cation. Anything is a molecular species. That's why rough example is M. M will be enclosed in box sometimes. Like this they will give. This is M plus 1. This is called collision peak. This is collision peak, and what is this? What is this peak? Molecular ion peak. Suppose if there is no collisions, if there is no collision, then if there is no collision, this peak disappears or not? If this peak is disappear, last peak is what? This one or not? Then last peak is a molecular ion peak. Clear? Okay. So examples, in this case see ethers, nitriles, nitroalkanes. Nitroalkane shows M plus 1 peak in mass spectrum. In mass spectrum, M plus 1 peak is appeared with these functional groups. Common use ether, nitrile and nitroalkane. These peaks will be common for these functional groups. Nitrile, cyanide. Cyanide belongs to nitrile. Nitroalkane, nitrobenzene. This all will show this kind of M plus 1 peaks. Clear? So that is about how to stabilize a molecular ion, then how to identify a last peak, molecular ion peak. Okay, 2 points we learn in this class, especially stabilities of molecular ion, Beeman order of stability, and how to recognize a molecular ion. Okay, so take one question. Right. So before going fissions involved in mass spectrometry, you need to learn some selective area. What is molecular ion? How to generate a molecular ion? How to stabilize a molecular ion? How to recognize a molecular ion? Okay, right. So in mass spectrum, last peak is a, option A, last peak is a molecular ion peak, molecular ion peak, isotopic peak, collision peak. This question given in set exam. D all. Last peak may be. What is the last peak in mass spectrum? In mass spectrum, last peak may be molecular ion peak, isotopic peak, collision peak, or all. All may be possible or not? All are exist. In mass spectrum, last peak is a maybe any one of this. Next. In mass spectrum, isotopic peaks represented by, how isotopic peaks are represented by? This is M plus 1, option C. M plus 2, option D, all. In mass spectrum, isotopic peaks represented by which one? Either M plus 1 or M plus 2. This is molecular ion with lighter isotope. M plus 1 nothing but what? Isotopic peak possible. M plus 2 also isotopic peak is possible. But M is always a molecular ion peak with respect to lighter atoms. Only lighter atoms should be taken here. Don't take heavier atoms. Right. Which of the following statement is correct? In mass spectrum. Which of the following statement is correct in mass spectrum? Which of the following statement is correct in mass spectrum? Okay, so mass peak at high mass region. Mass peak at high mass region is a base peak. Okay, B. Molecular ion. Molecular ion is a high intense peak. Molecular ion is high intense peak. Okay, next, intense peak is a base peak. Intense peak is a base peak. Intense peak is a base peak. Option D. Molecular ion peak. Molecular ion peak always appear at last. Molecular ion peak always appears at last. Which is correct statement among these four? Guess, if you understand the concepts and if you listen the videos 1 and 2, mass spectrum 1, mass spectrum 2 video, if you listen, you can give the answer for these two questions. This is in this class only we learn. Here few points we learn in last before 2 classes. Some points we learn even in this class. Is it first statement is right? Which of the following, the statement questions expected in mass spectrometry. Otherwise only intensity question, chlorine or bromine question is expected in exam, or fragmentation mode also expected. Which statement is correct for mass spectrum? Mass peaks at high mass region is a base peak? No. Last peak is not always base peak. Maybe it is a base peak, may not be a base peak. Last peak is not a base peak. Whichever is intense, that is a base peak. It may be middle, at last, anywhere. So this is a wrong statement. This statement is incorrect. Okay? Then, molecular ion is a highly intense peak. Is it every time molecular ion is highly intense? No. May be intense, may not be intense. Molecular ion may not be an intense peak. Intense means what? What is the meaning of intense? Intense means more stable. Every time molecular ion is more stable? No. Sometimes daughter may be more stable than molecular ion. This statement is wrong. Try to understand this statement. That's why try to listen clearly. Intense peak is a base peak. In mass spectrum, intense peak is a base peak. Is it right? Yes, this statement is right. Always in mass spectrum, whichever peak is very high in height, that peak is belongs to base peak. That statement is right. C is correct. Then see, molecular ion peak always appeared at last. Is it right? No. So this is wrong. That's why you need to learn the concept clearly. Otherwise, every point looks correct. Clear? This statement is wrong. Mass peak at high mass region is a base peak. That is wrong. Every time last peak is more intense? Every time can I write last peak with high intensity? No. Every time may be high intense, may not be high intense. Two possibilities are there or not? If two possibilities are there, this option is wrong. Clear? Are you able to understand? These are our few gate questions there. This is clear gate examination question. Clear gate examination question, very easy. But on that time, if you sit in examination, it is not easy. Statement looks little bit confused. But if you understand concept clearly, if you approach through basics clearly, then concepts are very easy. Once if you enter into core knowledge in mass spectrometry, these points are nothing. Very easily you can predict the answer without any hesitation. Now, which of the following molecular ion is highly unstable? Which of the following molecular ion is highly unstable? These all are molecular ions. Okay, here we need to write like this. Without writing this, it is also correct, because here only they mentioned molecular ion. Which of the following molecular ion is highly unstable? Which is unstable? C. Very good. More branches, more instability. Clear? Which of the following molecular ion having poor fragmentation? Which will carry poor fragmentation? Which of the following molecular ion having poor fragmentation? See how questions they will frame. You are in concept only but unable to recollect the points clearly if you don't know this. Which of the following molecular ion having poor fragmentation? Which will carry poor fragmentation? D. Poor fragmentation for which one? Stable or unstable molecular ion? Stable. Which among the following is stable, I am asking. Stable molecular ion will give less information. Which among the following molecular ion will give more information about structure? So indirectly you may ask many questions here. Poor fragmentation means less information about their structure. Different ways they will ask question. Which among the following molecular ion will give less information about their structure? Which will give more information about their structure? More information means more fragmentation. More fragmentation means unstable. There is a way of asking question. Here what he was asking? Highly unstable means more information about their structure. See, I am giving more information. My hand is this much of length, my leg is this much of length, my neck is this much of length, my eyes are this much of size. I am giving more information. If I give more information, can you write clear structure of my body or not? Yes. If I am not giving more information, can you write clear structure? No. That is mass spectrometry. Mass spectrometry nothing but it will give complete information about structure of a molecule. Where you are doing fragmentation, whether it is giving stable fragment or unstable fragment, etc. Right. Clear? So that is about some applications regarding mass spectrometry. In this class we discussed about how to stabilize a molecular ion. Later on, how to recognize a molecular ion. These 2 points are very important. First you target molecular ion. Because molecular ion is a reference for you. Left side of molecular ion, low mass region. Right side of molecular ion, high mass region. High mass region may be M+1 peak, isotopic peak, impurity peak. So less than this, fragment ion peaks, both are appeared. Okay. So in your next class, we will see what type of fissions are available in mass spectrometry. How many types of breakings are available? Homolytic fission, heterolytic fission and semi-heterolysis. These are the 3 possible fissions are there. And what type of molecules are involved in that corresponding fissions, we are going to discuss in your next class. Okay. So hope you understood. Try to revise that 3 videos regularly so that next class will be very easy for you. Conceptually, if you learn, concept is very easy. From anywhere in the particular chapter, if they ask any question, you can attempt. If you know the concepts clearly. Okay. So we'll stop here and we will continue in your next class. Okay. You can leave now.